everyone, I am Dr. Jagadha, Associate Professor in the Department of Mathematics. The topic we will discuss about problems on volume integrals. First, what is the definition of volume integrals? Next, the problems we will solve regarding volume integrals. First, the definition of volume integral, which is in the Cartesian form. That is, the capital F of R is nothing but F1i plus F2j plus F3k, where we can that F1, F2, F3, they are the functions of x, y, z. And the volume integral is dx, dy, dz. Now, the volume integral, which is given by the formula is integral over v f dv, which is equal to triple integral f1i plus f2j plus f3k. This dv volume, it is in 3 dimension. That's what dx, dy, dz. This is the volume integral formula, which can be written in such a way also. That is I into triple integral f1 dx, dy, dz plus j triple integral f2 dx, dy, dz plus k triple integral f3 dx, dy, dz. Problems? Evaluate. The first one is triple integral v f dv, where f equal to 2x plus y, the function which is given. Capital V is the closed region bounded by the cylinder z equal to 4 minus x square. This point we have to note down. That is the surface of the cylinder. It is in xz plane. And the planes, the bounded region, the conditions, x equal to 0, y equal to 0, y equal to 2 and z equal to 0. With this condition satisfying our cylinder, we have to draw now. So the first one is, which is given in the question we are writing, the closed region which is covered if x and z varies covering the area, that is OAB, our surface, this condition satisfying the curve which is framing the geometrical figure, that is a triangle, that is OAB, and y varies from here easily we can see y from 0 to 2. That's what which is written here. So this is our function, this is our curve condition, this is our bounded region to frame the conditions which are given in our problem. Next, we will draw the diagram. So we can see these 3 dimensions. We can name it as O. Here x is there, here z is there, here y is there. So x-axis, z-axis and y-axis. This is completely our z and x, xz plane according to our question. Next, there is your point on z-axis, that is we named it as A, and there is your point on x-axis B. Just we are adding the cylinders, the cylinder which is framed it. Now the point actually 0, 0, 4, 3 dimension we are, from which now here x equal to 0, from here we are substituting z equal to 4. So the coordinate is 0, 0, 4. The next one is Here x is there. If you substitute here z equal to 0, minus x square equal to minus 4. So x equal to, we are obtaining 2. Minus minus cancelled. So 2 comma 0 comma 0. And this from y which is given from our question 0 to 2. So from the origin, the coordinate 0 comma 0 comma 0, from 0 to 2 it is there. This is our curve which is given z equal to 4 minus x square, which is given in the question. Now this is a grouped one. So integral over Vf dv, that is a volume integral, we have to calculate it, for which we have taken the interior integration x dimension. The next we have taken z dimension, z axis, z direction. The last, the outer one is y we have taken. So the function is 2x plus y, dx, dz, dy. Now, when we are doing the integrations, the curved one, better if we keep the interior part, the solution will be more comfortable. Now we can see it. The function here, this we are going to concentrate, what I circled it. With respect to x, we are going to do the integration. So 2x dx, it's nothing but x dx, the integration is x square by 2. 2 getting cancelled, x square. Then y, which is written as it is, dx, the integration is x. From 0 to square root of 4 minus z, dz dy. So only the substitution is left over for the interior integration. So this is the last step we obtained. So now we will substitute in the place of x the upper limit. So our upper limit is square root of 4 minus z. So if you substitute in the place of x square root of 4 minus z, the whole square, the root is getting cancelled. So the leftover is 4 minus z plus. We are substituting in the place of x. So the x is replaced by square root of 4 minus z, that is our upper limit. Y we are retaining as it is. The lower part is the value, the lower limit value is 0. So in the place of x 0, here also 0. So completely the lower value is vanished. So this is the result completely regarding interior integration. The work is over. Next we will move to our middle integration with respect to z. That is 4 dz, 4z minus z, that is z square by 2, plus y. We are not going to touch that one. Treating y as constant as it is we have written. Whereas coming to the part of this, that is 4 minus z, the whole power 1 by 2. 1 by 2 is our n according to our formula, that is integral x power n. So n plus 1, 1 by 2 plus 1, that is 3 by 2. So the down we have to write 3 by 2, that's what it is written reciprocally 2 by 3. But it should be written 2 by 3, but here it is the negative sign how it is occurred. That is, after doing the integration, the interior one, we are doing the integration with respect to z, then coefficient of z to be considered. So the coefficient of z is nothing but minus 1. So that's what here minus is placed it here. From 0 to 4, the final, the dy we are not touching as it is we have written. Now 4 is z minus z square by 2 This, we brought it this 2 by 3, the negative sign, minus 2 by 3y, remaining all as it is, just we have written. Now, this is the last step. We are going to substitute in the place of z 4. It is replaced by 4. 4, 4, 16. Here also 4 square, 16 by 2, 8. Here, this we are not going to touch, only the place of z we are writing. So we can see it here. 4 minus 4, 0. That's what. So the upper limit regarding the value, the limit value 4, the work is completed. The limit formula between upper and lower limit, negative sign is there. So the lower limit value is 0. So when you are substituting the lower limit value 0 in the place of z, where I am putting the tick, completely it is vanished. Here z is taking the value 0. So now minus 2y into 4. Before that, here this is 4 power 3 by 2. That is 4 power 1 by 2. That is square root of 4. Square root of 4 is 2. 2 cube, it's nothing but 8. So the 8 into minus 2, which is becoming minus 16y by 3. So this simplification, 8 minus minus put together plus. So 16y by 3 of dy. So we reached the outermost integration which is left over. So the outermost integration is 8 into dy, 8 dy plus 16 by 3 is there, because y we are doing the integration, y square by 2, 2 into 3, it has become 6. So from 0 to 2. So we substituted the upper limit in the place of y, 8 into 2, 16, and 16 into 4, 64 by x. So taking LCM, we obtained 160 by 6, the lowest fraction form, 80 by 3. So now, this volume integral, we know it, the divergence theorem, the surface integral f dot d n ds, which is equal to volume integral divergent f dv. So the volume integral, which is equal to surface integral, that's what divergence theorem, in which our volume integral is playing the role. Now our question is, apply divergence theorem to evaluate the surface integral which is given, that is f dot n ds, which is given, and the surface of the sphere is x square plus y square plus z square equal to 4, that is r square, radius r equal to 2. Now the given the question, which is the surface integral, that is x plus z of dy dz plus y plus z of dz dx plus x plus y of dx dy, which is written here. Our f1, it's nothing but x plus z, f2 is nothing but y plus z, f3 is x plus y. So dou f1 by dou x. So if you do the differentiation partially, here x, the differentiation is 1, z is treated as, we are neglecting because we are concentrating only on x variable. f2, regarding y, we are doing partially because dou represents partial differentiation. Here the y is 1. Next, dou f3 by dou z. There is no z term at all. That's what the last dou f3 by dou z, the result is 0. Now we know it, this is nothing but del dot f. We can write it this format also, that is gradient dot f. It's nothing but div f, divergent f, divergent of our function f. It's nothing but dou F1 by dou X plus dou F2 by dou Y plus dou F3 by dou Z. So what we obtained it, for which we obtained 1, for this obtained 1, the last one is 0, we substituted and we obtained the divergent F, the result is 2. Because we need for our volume integral, this is the format of Gauss divergence theorem. This is nothing but the left side f dot and ds. This is nothing but divergent f dv. The dv only, this one, dx, dy, dz. Now we obtained this complete result 2 and dx, dy, dz as it is we have written. Next, dx, dy, dz replaced by dv, and volume of the sphere, we know it, 4 by 3 pi r cube. This is the volume of the sphere. Our r is 2. That's what the starting of the problem condition which is given. X square plus y square plus z square equal to 4. That is 2 square. That is r square, r equal to 2. So in the formula, r is replaced by 2, and here also it is written what is given in the question condition. So now 8 and 8 8s are 64 pi by 3. The sphere is, radius of the sphere is 2. So we obtained the result of this problem 64 pi by 3. So we will move to the next problem, that is using the divergence theorem to evaluate. Here the surface integral which is given, that is x dy dz plus y dz dx plus z dx dy. That is the surface integral which is given in our question. That is nothing but the surface integral f dot n ds. That is f dot n ds, which is nothing but our volume integral div f dv. So surface integral which is equal to volume integral, where s is the surface of the sphere, the condition which is given x square plus y square plus z square equal to a square. So a square, that is r square, our r is a. We will move to the solution. That is given surface integral, we are writing as it is here. The Gauss divergence formula, that is surface integral. Capital S denotes surface integral. Capital V represents volume integral. This completely nothing but f dot n ds. Otherwise, another format we can write f1 dy dz plus f2 dz dx plus f3 dx dy, which is equal to dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z dx dy dz. So according to our equation, our f1 is x, f2 equal to y, f3 equal to z. So dou f1 by dou x. So we will do partially with respect to x. The value is 1. Dou f2 by dou y, partially we are doing. So the value is 1. Dou f3 by dou z we are doing. Partially the value is 1. Now put together dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. It's nothing but divergent f, that is our grade dot f. All the values we are substituting in the particular places, which is equal to 3. That is capital V is the volume of the sphere with the radius a. That is our volume, which is equal to 4 by 3 pi r cube. Now our given condition, we know it, x square plus y square plus z square equal to a square. So our r is a. So in the volume of the sphere formula, 4 by 3 pi r cube. R is replaced by our given problem radius A. So we replaced it, but our surface integral, which is equal to our volume integral. So the volume integral is the result divergent F, we got it. That is 3 into V. So V is nothing but our 4 by 3 pi A cube. So 3 getting cancelled. The final result we obtained for this particular problem, 4 pi A cube. Next, we will move to the next problem, that is using divergence theorem. That is evaluate, that is we can see the surface integral f dot n ds. Here our f equal to x cube I plus y cube j plus z cube k, and s is the surface of the sphere. X square plus y square plus z square equal to r square. So what we are going to do, that is the surface which is given, that is here, is there. We have to calculate a surface integral for which the vector function which is given here. But what we are going to do, instead of surface integral, we can find the volume integral, because our divergence theorem, the condition is surface integral which is equal to volume integral of divergent F. So that technique we are going to use, we are going to evaluate volume integral. Now, so the divergent F, that is grade dot F. Our grade dot F, it's nothing but divergent F. The grade is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z dot our vector function. So if you do this dot product, we obtained this result. That is, our result is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So our f1 equal to x cube, that is looking at our equation, we can write it, so we can see it. So the next one is f2 equal to y3, next f3 equal to z cube. So now dou by dou x of f1, that is f1 is replaced by x cube, dou by dou y of f2, that is y cube, dou by dou z of f3, that is z cube. So we will do now the partial differentiation. The first one with respect to x we will do it. So with respect to x, that is x cube which is there. So the x cube, the differentiation is, that is partially with respect to x, 3x square. This is also the y cube partially with respect to y, that is plus 3y square. The last one is partially with respect to z is 3z square. So in which the 3 is common, we have taken out. So the 3 of x square plus y square plus z square. So now our volume integral formula is integral over v divergent f dv. That is triple integral v 3 of, here what is the result we got it, our divergent f, that is 3 of x square plus y square plus z square. The dv, which is replaced by the 3 dimensions, dx, dy, dz. Now this is our in Cartesian form. We are writing in now r equal to 0 to the limits we are writing. We are converting into polar form to do the integration in a very simple manner. Mostly when the sphere, circle, they are there, we will be very more comfortable if we go under polar form, for which we can say it our radius, that is x square plus y square plus r square equal to, which is given in our question, a square. So r from 0 to a, our spherical coordinates, the theta, the angle is 0 to pi, whereas pi is 0 to 2 pi. Now we are replacing this in the form of x, y, z, the dimension. We are going to convert it into r, theta and pi, for which the interior one, pi from 0 to 2 pi, the middle one 0 to pi, the outer one is 0 to a. This 3 we kept it outside. Now the totally x square plus y square plus z square, which is nothing but r square. This complete dx, dy, dz, which is replaced by r squared sine theta d pi d theta dr. This complete, we replaced it. This is using Jacobian or dx, dy, dz. The Jacobian formula applying, we obtained, this is the result. Now, here r square is z, here r square is z. Put together r power 4. So we can see it, r power 4 sine theta, that is comparing the previous step. This is the middle integration and outermost integration, the outside 3. Only the changes we brought it, r square into r square, which is written r power 4. And the sine theta, we wrote it as it is sine theta. Only the d pi, the integral we are doing, we obtained the result pi. From 0 to 2 pi, that is the limit, the range of interior integration, 0 to 2 pi. This d theta dr, we didn't bring any changes at all, as it is we have written. So this interior integration limit value we applied in the place of pi, that is upper limit, that is 2 pi, limit formula, lower limit is 0. This 2 pi, we brought it outside, 3 into 2 pi, 6 pi, integral over r equal to 0 to a, here integral over theta from 0 to pi. Here we can write it, the r power 4, just we brought it front of the integral. So the next here, sine theta, d theta, dr. So now 6 pi. Here, the outermost integration 0 to a, r power 4. Now we are concentrating the middle integral with respect to theta. So when we are concentrating the middle integral with respect to theta, the middle one is sine theta. Sine theta integral is minus cos theta. So we can see it, the cos pi, the value is minus 1. Already minus is there outside. We can see it, this is the upper limit value is substituted, limit formula, and here minus cos 0 value is 1. This is 1 plus 1. So that's what here, 1 plus 1, after substituting the middle integration, 0 to pi, we obtained the result. The 2 into 6 pi put together, we have written 12 pi. So we are going to concentrate the outermost integration, that is from 0 to a, r power 4 dr. So r power 4 dr, which is equal to, we can do the integration, that is r power 5 by 5 from 0 to a. So in the place of r, if we substitute, then a power 5 by 5. So we obtained the result 12 pi a power 5 by 5. So this is the problem, that is using divergence theorem, evaluate The surface integral which is given, that is f dot n ds, that is a formula for the surface integral, where our f is playing a role in our problem is y square z square I plus z square x square j plus z square y square k dot n ds, where S is the surface part of the unit sphere above the xy plane. Now, this is our f, that is y square z square I plus z square x square j plus z square y square k. Now we have to evaluate, it is given surface integral, but we are going to do the volume integral, because using the divergence theorem, surface integral, that is f dot double integral over surface double integral over s f dot and ds, where f is playing the role vector function, n is playing the role normal vector, ds the surface which lies in which plane. So the complete the surface integral, which is equal to our volume integral. Our volume integral is triple integral V. The capital V represents our volume integral. So divergent F. The divergent F only here, which is given dou F1 by dou X plus dou F2 by dou Y plus dou F3 by dou Z, and dV. The dV in the sense in 3 dimensions, dx, dy, dz. First, when we are comparing our vector function, that is our f, here our f1, which is playing the role y squared z square, and f2 is z square x square, the last one f3 is z square y square. So f1 equal to y square z square, f2 equal to z square x square, f3 equal to z square y square. Now we will do dou f1 by dou x. So dou f1, that is f1, which is replaced by our term y squared z square. Next, dou f2 by dou y, that is our f2, which is replaced in this particular place, in the place of f2, which is replaced by z square x square. Next, dou f3, which is replaced by z square y square. Now we have to do partially the first term with respect to x, but unfortunately there is no x variable at all, so that's why the result is 0. When we are moving to the second integral also, we are noticing there is no y term. So here also it is 0. Whereas finally we are seeing that is z square y square. So z square we have to do partially with respect to z. So z square is 2z, y square, even though it is another variable, it is treated as constant. So 2z y square. So the integral over v, div f dv, we have to find the volume integral. So the triple integral v, the divergent f, just now we obtained it, 2z y square. So in the place of divergent f, we replaced it 2z y square, dv, which is replaced by dx, dy, dz. Now, to do this integration, we have selected mostly circle, and this is also sphere, so we will go for a polar form. So x, we are going to replace by r sine theta cos pi, y, which is replaced by r sine theta sin pi, z is replaced by r cos theta. So we have to here the two as it is. Z we are going to write r cos theta. Y is r sin theta sin pi, but y square is there. That is the reason r square sin square pi. This dx, dy, dz according to our formula Jacobian using, before that we can see the limits of this sphere, that is the limit from r 0 to 1 and the angles 0 to pi and pi is 0 to 2 pi. This just we discussed it, that is what we obtained it. Our we can say here, that is z is replaced by this one, y square which is replaced by squaring of this term, and this is Jacobian of. So that's what here which is seen here, the Jacobian of that dx, dy, dz, we obtained r square d pi d theta dr. So the two we put it as it is, and the interior integration is pi from 0 to 2 pi. The middle integration is 0 to pi. The outermost integration is 0 to 1. Now, where the r are there, r power 1, r square, that is r power 5. Next, the cos theta as it is, sin square theta as it is, sin square pi, this is as it is, d pi d theta dr. Now, what we are going to do is, this two outermost middle one as it is written, r power 5 cos theta sin square theta, this interior integration pi from 0 to 2 pi sin square pi d theta dr. We are going to focus only this one now. But sine, it has the power, that is sine square. When the trigonometric term, if they have power relevant formula, we will replace it. For that, we replaced it. Wherever I am putting the ticks, comparing with the previous step, there is no change at all. Only the change we brought it where I am putting the circle. That is sin square pi, which is replaced by our relevant formula, that is 1 minus cos 2 pi by 2. So in which this 2 and this 2 we can cancel it. Now the outermost one, the middle one, and the interior one, just we have written, and this is also we have written as it is, r power 5 cos theta sin square theta, here 1 minus cos 2 pi d theta dr. This integration to be done now. We didn't do the integration, just we replaced it the sin square pi, the relevant trigonometric formula. Here 1 into d pi, the integration is pi, and cos 2 pi integration is sin 2 pi by 2. So we substituted the limits, we obtained it 2 pi. Next, this 2 pi, we brought it outside. This is the outermost integration, that is from r equal to 0 to 1. This is the middle integration from 0 to pi, r power 5 cos theta sin square d theta dr. This integration, to do it is very difficult, for which we are going to apply a formula, that is, here this sin theta, we are going to take it as f of r, Then f dash of r should be there. Yeah, it is there, cos theta. Completely it is in this format of this formula. That is f of r sine theta. Our n is playing the role 2. This is f dash of r. So we can write it f of r power n plus 1 by n plus 1. Our n is 2. So substituting in this formula, integral formula, we obtained the result sine cube theta by 3. Here once again 0 to pi, but sine cube theta, again sine, it is in cube, the trigonometry. So the relevant, the formula, we are substituting, that is 1 by 4 of sine 3 theta minus 3 sine theta. So the formula which is replaced in the place of sine cube theta, that is 1 by 4 of sine 3 theta minus 3 sine theta, 0 to pi. The theta which is replaced by our upper limit, pi. So sine n pi, we know it is 0. So the upper limit in the place of theta we are substituting, it has become 0. What about the lower one? The lower one, theta place we are going to substitute 0. Sine 0, we know it 0. Completely the middle integral, the value which has become 0. So the middle integral, everything, the result when it has become 0, 0 into anything. So we are not doing the outermost only. We are going to stop the problem up to here. Because the middle integral value is 0, 0 into whatever we are going to get the outermost one also 0. In that angle, this problem is coming to an end. Now, we will come to a conclusion of this topic. That is, first we have taken a function f equal to 2x plus y and z equal to 4 minus x square, that is the surface condition which is given, and this is the bounded region to frame our cylinder. That is x equal to 0, y equal to 0, y equal to 2 and z equal to 0. One important point to be noted, that is our surface which lies in xz plane, according to that the dimensions naming part we have to take care. Then we moved your problem, that is surface integral. In the surface integral, f dot n ds which is given. For that, the sphere condition which is given, x square plus y square plus z square equal to 4. That is r square, r equal to 2. This problem we concentrated. Next, we moved to another surface integral. Here, we didn't calculate at all surface integral. But in the question which is given, evaluate surface integral. But we did volume integral using Gauss divergence theorem. That is Gauss divergence theorem, surface integral which is equal to volume integral of the divergent of that particular function. Now, this problem also, the function which is given, x dy dz plus y dz dx plus z dx dy. So x square plus y square plus z square equal to a square. Here our radius played a role, a. Next we moved. Here vector point function I, j, k. They are mutually perpendicular vectors. The components, that is f vector point function. This is f1, f2, f3. That is x cube, y cube, z cube. They played a role, f1, f2, f3 respectively. Then the condition of the sphere, x square plus y square plus z square equal to r square. The radius is r. Here also we used the volume integral. And next we moved to our problem, that is surface integral. Here which is given f dot n ds. This surface integral, here f, our vector point function, is y squared z square I plus z square x square j plus z square y square k dot n ds. Any format they can give. F dot n ds they will give, otherwise different way. Here also we have seen here totally the function surface which is given, otherwise this format given also we can use it, our volume integral which is equal to surface integral, that is divergent of the particular function over the volume integral in 3 dimensions, that is dv, which is nothing but dx dy dz, for which here the sphere, that is our radius which is given unit, that is here we can see it unit sphere. The before the problem and all, which is the picture which is very clearly given. So this problem which is given r square equal to 4. The next problem r square equal to a square. Here r square is r square, whereas when we concentrated the last the problem unit sphere, that is 1. And one particular the last problem we stopped in the middle integration only because the middle integration, this particular problem, the value we obtained, the result what we obtained is 0. So we didn't further towards the solution, we didn't move at all. Anyway, the outermost integration, if we concentrate also, the result is going to be 0. So completely we discussed through this video lecture problems on volume integrals. Thank you very much to you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.